In this video, we're going to compute the arc length of one arch of a cycloid curve. Now, the cycloid curve can be constructed geometrically by marking a spot on the edge of a circle, and as that circle rolls along a straight line, the spot traces out the cycloid function. And I'll post a link real quick to the video where I animated this and derived the parametric equations for a cycloid curve. In this video, we're just given the equations. X of t is 2t minus 2 sine t, and y of t is 2 minus 2 cosine t. In the interval 0 to 2 pi for the parameter t, that does indeed trace out one full arch of the cycloid function. And we're trying to get the arc length here, and the derivation of arc length is so quick in parametric equations that I think it's worth repeating. So in the picture, I just marked a little section of arc called ds, and ds can be broken into components. We call the horizontal component dx and the vertical component dy. And then I just apply the Pythagorean theorem, and I have ds squared is dx squared plus dy squared. We square root both sides. All right, next we factor a dt out of the square root. In other words, we divide by dt squared inside the square root and multiply by dt on the outside. And then we realize we can write dx squared over dt squared as dx dt all squared. Same thing for dy dt. And now that we have ds expressed in terms of dt, we can just add all of these up using an integral. The total arc length is the sum of all the contributions to the arc length. And I'm going to write dx dt as x prime of t. So I have the first derivative of x with respect to t squared. Similar for the y term, dt. And to get the total arc length, I go from the starting value of t to the finishing value of t. So I'll write just t1, t2. So there's the arc length formula. And it looks like what I should start with is computing the derivative of each of these parametric equations. So I get x prime of t first, and that's going to be a 2 minus 2 cosine t. And then y prime of t is positive 2 sine t because the derivative of cosine produces a minus sign. So now I need to set up an integral from the starting value of t to the finishing value of t, and then square root of the sum of the squares of these derivatives. And then the next step, I'm going to go ahead and expand this squared binomial 2 minus 2 cosine t. That gives me 4 minus a 4 cosine t minus another 4 cosine t, so minus 8 cosine t. I'm just doing FOIL here, plus 4 cosine squared t. And then the second piece gives me a 4 sine squared t. Then I notice that I can apply a Pythagorean identity here. I can factor a 4 out of the 4 cosine squared plus 4 sine squared, and cosine squared plus sine squared is just 1. In other words, this term right here reduces to 4. And when I combine it with the 4 out in front, that gives me an 8. So now I have the integral from 0 to 2 pi of 8 minus 8 cosine t dt. I'm going to do one more thing to clean it up before we get serious about the integral. I'm just going to pull out that 8 inside the square root. That gives me a square root of 8, which is 2 root 2, and I can pull that out in front. So 2 root 2, integral from 0 to 2 pi, square root 1 minus cosine t dt. Now there's a couple different approaches to this integral, and it's actually really easy to get yourself in trouble with some tricky sign issues. I ended up making a whole separate video just for this integral and looking at it in a couple different ways, and I'll post a link to that real quick. And one of the results in that video is that it turns out to be easiest to evaluate this integral if I use a trig identity to get it done. And I'll go ahead and figure this trig identity out up here. So just a little reminder, sine squared of theta is 1/2 1 minus cosine of twice theta. And I see that 1 minus cosine of something there. So that's what I'm trying to isolate and express as 1 minus cosine of t. So I have 1 minus cosine 2 theta is 2 sine squared theta. Now I replace theta with t over 2, and I get 1 minus cosine t is equal to 2 sine squared t over 2. So that's my next move here. And I can pull a root 2 out of that and combine it with the root 2 out in front to give me 2 times 2 out in front. So that's now a 4. And then I have the square root of sine squared t over 2. So we could be flippant about it and just say the square root undoes the squaring. So I could just get sine t over 2. But one of the points that I was making in the separate video that I made on this integral is that there are cases where if you're too casual about it, you can end up getting a sign error. And the issue is that the square root of the square of something is actually the absolute value of that thing. It must always be positive. So if we're looking at a region where the sine function is negative, the square root of sine squared is not going to be equal to the sine function. It's going to be the negative of the sine function. So we're going to just double check real quick. Look at the argument of the sine function and make sure we're only looking at values of t that give us positive values of the sine function so that we know this statement is true. And because my interval is from 0 to 2 pi, the biggest the argument of the sine function ever gets here is pi. In other words, as we go from t equals 0 to 2 pi, the sine function is always positive. This is the first bump of a sine wiggle that's above the t-axis, so we're cool. Now I can just set this thing up to guess the antiderivative. I would like to have a factor of 1/2 inside the integral. That's the derivative of the interior. It makes it easier to think about the chain rule backwards, but that means that I need to multiply by 2 out in front. So that gives me an 8 out in front. And then the antiderivative of 1/2 sine t over 2 is going to be a negative cosine t over 2. And I'm evaluating this thing from 0 to 2 pi. When I plug in the upper limit, that gives me 8 times negative cosine of pi. And then the lower limit, I would have a plus cosine of 0. And the cosine of pi is -1, and the negative of that is +1, and the cosine of 0 is another +1. That gives me 2, so I have 8 times 2. And finally, I get the arc length of this cycloid arch as 16, and we're done. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.